This is Chapter 13, Climate, Weather, and Their Influences on Geology, Lecture 2. We left off on Lecture 1 with the causes of seasons on Earth, and we'll shift now to looking at rainforests. So, rainforests are extremely lush environments. They are critical ecosystems because they contain more than half of the terrestrial life on Earth. And they have high rainfall, no freezing temperatures, a lot of plants. They're tropical, temperate. Let's see. They can occur in the tropics, like I said, and then in special circumstances in temperate climates that are not tropical. Um, of course, most of them are in the tropics. They're associated with the Intertropical Convergence Zone, the ITCZ. That's a line found along the equator where the northeast and the southwest trade winds converge. And then the location of the ITCZ brings low pressure and immense rainfall. We also have just some basic info on their structure. You've got the forest floor, the understory, and then the canopy. And when I was a kid, my favorite thing was like this little cartoon guy called Spin, I think. He had a program about rainforests and he explained all this stuff. I don't know. If I can find it, I will link it in our page somewhere because it was cool. But with that, here's a visual on the ITCZ. You can easily compare the location of that and the rainforest in green. So there's a correlation here. By the way, we do see temperate rainforests in the Washington State area. We don't. Yeah, we do have it mapped there. Just checking that out. All right. So why are rainforests disappearing? One big thing is commercial logging. That consumes large areas of the rainforest. It's generally going to involve clear cutting, so no more forest, just open land. Natural resource exploration, such as mining, can strip away the rainforest because you're destroying tracts of land that way. In fact, it might be logged first and mined second. Cattle ranchers are also kind of pointed out as impacting rainforests because they have to remove the rainforest to make space for pasture grasses and the cattle themselves. If you build roads, construct highways to support industry, that can understandably destroy parts of the forest. Construction of a dam can be important for hydroelectric power and water resources, but it also destroys the areas because you've just changed the way the land looks. And then just farming. If you clear the forest for farming, you're losing the forest. Okay. So by contrast, here's the location of deserts and other arid lands across the globe. Deserts are dry lands that receive less than 25 centimeters or 910 inches of rain per year. The Earth's large deserts are the result of descending air in subtropical belts and from airflow that moves across cold ocean currents. So deserts can also form in the rain shadow of mountain ranges, as I mentioned before. We'll look at some settings. All right, so you can have coastal deserts where cold upwelling ocean currents cool the air and decrease its ability to hold moisture. You can have subtropical deserts. You have general atmospheric circulation bringing dry air into the subtropics. That's the case in the Sahara. All right. And then rain shadow deserts, again, that's where moist air rises over the mountains, it rains, and as the air descends on the downwind side, it dries out. So the Patagonia Desert is an example of a rain shadow desert. You can also have continental deserts. Those form in the interior of some continents, far from sources of moisture. Gobi Desert would be an example. And then polar deserts form where cold, dry air prevails. Any available moisture that they would have is frozen most of the year. So you have in Antarctica the dry valleys as an example. All right, and then desertification, where land can become desert that was previously not desert. Okay, so here's some areas at great risk in red. Desertification is the process of converting other lands to deserts, primarily through drought, mismanagement, and misuse by humans. It can occur from overgrazing, poor farming techniques, diverting surface water, soil loss, and regional climate change. So areas most at risk, we have the western U.S. and Great Plains. And then we have Sahel in Africa, the Middle East, and parts of Australia. Okay. Can't think about all this without thinking about sediment and sediment transport. We'll look at how wind transports sediment and other materials. Most materials on the Earth's surface are too heavy or too attached to the Earth's surface for the wind to move them. But sand grains can be picked up by strong winds. The grain is then launched and then it falls down, sometimes skipping along the ground. A process called saltation. Okay? Finer sediments such as dust, silt, and salt can be suspended in flowing air, and then they can travel thousands of kilometers. I have a chart down here that shows height and then wind speed, with wind speed decreasing with height, like that, over the treetops. And just keep in mind, again, wind can move sand close to the ground and then carry dust higher and then farther. And that's a good transition to dust storms and whirlwinds. Okay, so in desert settings like the southwest U.S., dust storms are common around thunderstorms. We're seeing that here. In Arizona, for example, you can have something called a whirlwind. Those are rotating columns of wind that are typically tens to hundreds of meters across and then less than 1 kilometer in height. Sometimes they're called dust devils. Fun fact, these have been observed on Mars as well. We'll think about wind erosion as well. Okay, so blowing grains of sand and ice can shape loose stones or bedrock. This is in Peru. And wind can remove loose material such as sand and not held down by the roots of these plants. You see it kind of staying there. And over time, things become progressively weathered and eroded with wind. Okay, so then where does all this sediment accumulate? Well, active sand dunes. This is in Death Valley, California. These are stabilized dunes. They're not moving around like these ones in Death Valley are so much. That's in New Mexico. You can also have wind streaks. Like in Namibia, we see kind of a prevailing wind direction, probably from that way. And then wind-blown silt, we call that loess. There's a few different types of sand dunes, believe it or not. We have a crescent shape where the wind is from this direction, or parabolic, impacted by the presence of vegetation here. All right. A star pattern could be found where there are multiple wind directions. Transverse, that is from one dominant wind direction as well. All right. And those linear dunes that you see there are just forming perpendicular to the prevailing wind direction. With a longitudinal pattern, linear dunes form parallel to the overall wind direction. And then with a, say, composite type, here you have aspects of a few different types of dunes, giving you, not just one shape here. We'll look at that again with some real examples. All right. Okay. Shapes of dunes and cross beds. Dunes actually have a steep side. We can call that the slip face on the downwind side. It's also referred to as a lee side. And that's what gets preserved into the sedimentary and later rock record, because you have grains from this side constantly being moved up and being deposited on the slip face or lee side. And you can see everything in that direction. And wind truncates the top of the dune, like continuously supplying more and more sand that will eventually be deposited onto the lee side. And those are preserved as cross beds. So by looking at this diagram, I can still tell that the wind direction was coming from the left. Okay. There's some landscape features we can see that are characteristic of deserts. The first is an alluvial fan. That's where loose rocks are transported from mountainous areas in streams and deposited in fan-shaped aprons. So you have to have somewhat of an elevation change to get this feature. This is in Death Valley. You can have a desert wash. Normally these areas are dry, but the washes can fill rapidly with water during a rainstorm, which also carries sediment. A playa, that's a shallow, closed basin that receives runoff but has no outlet. And this is in Death Valley as well. So putting that together, you can see fans, washes here, and then a playa as well. And then sand dunes, because sand is not held down by vegetation in this case, and there has to be a sufficient supply of sand for them to form as well. This is in Namibia. Okay, so features that develop over time in deserts, you can have a pediment. That's a gently sloping erosional surface. This is in Joshua Tree National Park in California. Desert pavements, that's where rocks are concentrated on the surface because all the finer materials have been blown or washed away. This is in western Arizona. You can also have caliche. That's where soluble minerals in water percolate down into the soil. The water then evaporates and the minerals stay behind, which actually coats the grains that are there in central Arizona. We might also see desert varnish. That's where exposed surfaces get coated with iron and manganese oxides, forming a dark natural rock varnish. And this is in New Mexico, in the Three Rivers Petroglyph site. We might also see what we call natural stains. Those are vertical streaks of red, brown, and black deposited by water that flowed down the rock face and evaporated. And this is the Yampa River in Utah. Let's look at some hard evidence of climate change over time. So these are temperature anomalies over time. We see a general increase in the global average air temperature beginning around 1890. The anomaly is the difference between a value and the average of that value. We see a similar, let's say a very similar sea surface temperature warming since 1910. So there's some anomalies in the top diagram that show trending upwards. Getting into about 1980 is where we really see it take off with the anomaly data. All right, evidence of climate change, part 2 here. Satellite measurements also record times of warming, cooling, and a little change in temperature. We can correlate these changes to various types of events. So in this case, we have the temperature departure from 1981 to 2017 on average. So that's over time. Let's see. We have a cooling event. We have El Nino warming. And we can kind of see what has changed over time in very recent history that way. But we can use other types of data called proxies to reconstruct temperature before thermometers even existed, such as tree rings, showing how long our warm growing season was versus our cool season. And then isotopic data from cave deposits and fossils can lead us to indications about temperature conditions. All right, let's talk about insulation. Nearly all of Earth's heating at the surface comes from insulation. Some insulation is absorbed by the atmosphere. That's our orange disks there. Insulation is also absorbed by clouds, soot, and fine particles. We call those aerosols. And then some of it radiates back into space as long-wave energy. We call that infrared. Some insulation is also reflected to space from the land surface and oceans. There's a few factors affecting climate change, and we have a couple parts to this. All right, so we have data from the Mauna Loa Observatory in Hawaii. That is the parts per million of carbon dioxide over time. And within that, you'll see an annual cycle. We're sort of zooming in on this part and showing you there's a rise from January till about May, June, and then it goes back down to August and starts to rise again. So greenhouse gases like water vapor and carbon dioxide absorb the heat that's radiated from the Earth, and that warms the planet. This top graph is showing that atmospheric CO2 has increased steadily since 1957. Human activities that release carbon dioxide to the atmosphere have also increased in intensity over the same period of time, which leads most scientists to link the recent global temperature to an increase in human activities. There is a correlation here. And then with this graph, we have CO2 with many years before present through ice core analyses. That would indicate that temperature and carbon dioxide change together during ice advances. So more ice. Oscillation, of course, within a given year is caused by the natural change of seasons. All right. Say in the northern hemisphere by March, April, many trees have been dormant and in some cases leafless for many months, and they were unable to remove carbon dioxide from the atmosphere during their buildup of biomass. And then by September, These trees have had many months conducting photosynthesis and accumulating biomass, so CO2 is removed from the atmosphere. Okay. If you actually had similar amounts of forest in the northern hemisphere and the southern hemisphere, you wouldn't see this oscillation the way that it is here. There wouldn't be such a change. All right. So from the ice core analyses, we have an inferred temperature that goes up and down, and then a CO2 concentration that goes up and down as well. And we can say that these correlate fairly well. All right, part 2 here, factors affecting climate change. So climate is always changing, and many factors cause climate to change. Being a geologist, I try to have a long perspective, right? All right. Ocean oscillations, those refer to times usually lasting for a few decades when particular ocean basins are warmer or colder than normal. And then these ocean oscillations affect the global air temperatures because the oceans are so large. We don't have a good handle on why ocean oscillations occur or how we can predict the onset of a period of warming or cooling with ocean oscillations. But we have names for the different ones too. All right, more on ocean oscillations. So this is the Atlantic multidecadal oscillation. And you have a departure shown here from warmer to cooler. The point is that oceans change from cool to warm phases, and those are our ocean oscillations. They're marked by changes in atmospheric pressure, wind circulation, and sea surface temperatures. And the warm and cold phases can last a year or so in the case of El Nino, or decades. The most important ones that would influence climate change are the Pacific decadal oscillation and the Atlantic multidecadal oscillation. So that's what we see represented here. We're currently in a warm period, and there's a clear correlation with temperature changes such as highs in the 1930s and the 1940s, and then cooling in the 1970s into more recent warming. Okay. We'll look at this region and consider how warming temperatures would affect different aspects of it. Well, if you up the temperature, you'll melt snow and ice. You'll increase runoff and decrease the salinity of the ocean. And that'll affect vegetation. We could have a drought, which leads to desertification, as well as changing amounts of CO2 in the atmosphere. It's no longer taken up by plants at the same rate. This can change evaporation, kind of increasing evaporation, the direction of ocean currents, and ocean oscillations. It can also affect the formation of sea ice, the lack thereof, ocean salinity, and then thermohaline circulation. It'll also change the amount of clouds, precipitation, or severe storms over time with greater temperatures. So let's think about the implications of climate change. We have a depiction here of the decrease in sea ice in the Arctic between 1979 on the left and 2003 on the right, while the planet was warming. So melting of sea ice does not affect sea levels, but it does decrease the albedo of the surface, the habitats of Arctic creatures, and the salinity of the underlying seawater, which can affect the thermohaline circulation pathways. So we've talked about hurricanes perhaps being quite larger with more warm vapor. Climate change can then affect the frequency or strength of severe storms. So we have at the top the annual number of Atlantic storms and hurricanes from 1880 to 2014. We're seeing a few more tropical storms over time. It's kind of unclear, but it appears the hurricane data has gone up a bit as well. Just looking at this. We also know that temperature has gone up, so there appears to be a correlation there. On the bottom, we have the number of tornadoes, number of strong to violent tornadoes over time, beginning in the 1950s till now. Honestly, looks like, let's see, with rising temperature, we're not seeing a huge amount more of strong tornadoes. So in a way, that's pretty good, right? There was a lot in this time period from like 1954 to 1970s. And there's still a fair amount, but this is where we see the spikes, which is interesting. Well, let's think about plate tectonics and how those affect climate as well. We've already talked about how mountains influence regional climates because mountains intercept wind and water vapor, causing rain shadows and other climatic effects. Tectonic uplift also exposes land to chemical weathering, which then removes carbon dioxide from the atmosphere. So with seafloor spreading, rapid seafloor spreading displaces water from the ocean basins, and then such flooding could change local climates. We're seeing a flooded place here. Volcanoes, like with volcanic activity and eruptions, that releases carbon dioxide and water vapor, which can warm the atmosphere. Can also give you a lot of dust particles, which messes up your growing season and could result in some cooling as well. So, how could climate change as a plate moves? We're looking back 260 million years ago to the Permian, where North America was part of a supercontinent. The Appalachian Mountains were young, newly uplifted. They would have caused huge rain shadow deserts to the west. And then in the Cretaceous, 75 million years ago, shallow seas were all across North America, this Cretaceous seaway. The climate was likely pretty warm and wet over the exposed land. These seas weren't very deep, you can see, because they're lighter in color here. And then into the Neogene, only 20 million years ago, the rise of our coastal mountain ranges to the west in North America would have likely blocked prevailing winds, causing increased rainfall along the coast and then rain shadow deserts inland. All right. So how does climate then affect tectonics if tectonics affect climate? So we'll think about the rate of erosion. It's related to climate, so it affects the height of the uplift. Continental collisions produced extremely high mountains, which force wind belts to flow around and over them. Uplift leads to erosion, which acts to lower the mountain range, again affecting the climate. You can have what's called an episode of imbalance. So solar heating on the Tibetan Plateau causes heated air to rise, drawing in monsoon moisture toward the mountains, causing intense rainfall. And then with that, intense erosion may allow lateral movement of material in the Himalayas, like along these faults. So movement along faults, made a little bit of earthquake activity, and then changes to the structures here. All right. Hurricane Sandy. We have it pointed out here in the Atlantic. That began as a tropical cyclone that moved up the East Coast in October 2012. It encountered a cold front and mid-latitude cyclone coming in from the west. With that event, we had a lot of coastal erosion and wind damage. As you can see here, it's not good. We can observe the progression of Hurricane Sandy through time and identify processes that are occurring in different areas. So it started in the tropics, moved west, and then turned north. And then it had that cold front to the west, the Arcuate cold front. It moved up the east coast. It stayed over water and within warmer waters of the Gulf Stream, which is kind of right about here. And then it merged with the cold front and came on shore in New Jersey while weakening from hurricane status when it merged with the cold front. So it was sort of fueled by that warm water vapor, had a lot of strength that way, but eventually dissipated when it merged with the cold front. That puts a few things together, and we will stop there for this chapter.